Good morning and welcome folks to our introduction to checking and auditing said submissions with InfoDrainage. Thanks for joining us. Still got quite a few coming in, so what I plan to do is Peter Coombs here, so thanks for joining. I'll introduce the team who are on the call. Mike Reeves is the main presenter today, and just to mention, what we'll do is we'll run through the session, which is just under the hour, and you'll notice that you're all muted because we've got quite a few people that are online, so it'd be a little bit too noisy if we had you unmuted, and there are still people joining as we speak. So what we'll do is just ask you to post and pose any questions in the questions pop-up that you'll see in the little pop-up screen that you've got. So if you post a question, then we can run a Q&A. We've got an extra half an hour at the end of the presentation to run through the Q&A for you. Before we start, what I'd like to do is just make sure that everyone's aware as to what InnoVise actually do. Very interesting when I'm sort of talking to people, in that they don't quite realize what InnoVise underpins and supports in terms of the entire built water cycle. So this diagram here just shows you our actual involvement throughout the whole water cycle, starting with source water. This is like a meandering diagram that runs from sort of top left down to sort of bottom right. So from the source of clean water in the first instance, we have artificial intelligence that helps the water companies to optimize the energy and the chemical dosing on their water treatment plants whilst maintaining water quality. And then that water gets fed into the distribution network. So we have technology to design and also model the water distribution networks right up to the doorsteps. That water gets consumed and generates wastewater, and you'll be very familiar with microdrainage as being the design tool to take that wastewater down to a public sewer, and those public sewers all interconnect and then feed down to wastewater treatment plants. But we have software technology to not just design, but to model these wastewater systems. And we have the artificial intelligence to, again, optimize the running of the treatment plants to ensure that the quality of the water that we discharge back to the environment is of adequate quality. And overall, when you're managing all of these networks, we have asset management software as well. So we are extremely aware of the limitations of what we're doing. And the reason why I want to mention this is because with sustainable drainage systems, we are dealing with the consequences with the modeling software and the flood mapping software globally. And we can do a lot more earlier in the process to do with surface water management. And with the latest standards, the design construction guidance that's replaced sewers for adoption, the reviewing of the national, the non-statutory technical standards, etc., it's all leading us into looking at the impact of a development upon the existing catchment and the impact of the existing catchment upon the new development, both pre and post-development. We need to plan out the drainage systems better and understand the consequences of failure better. So that was the reason for sharing that with you. And also, just to mention before I hand over to Mike, that we do have something which is called the user feedback forum. We often call this the user voice, where people can go and with each of those solutions, whether it's managing the drainage assets, designing the drainage, looking at the artificial intelligence, whether it's water distribution, potable water distribution, storm sewer and flood modeling, or operational analytics that we're also involved with, there's an opportunity for the customers to actually go there and vote or raise any kind of issues that they'd like implemented within the technologies. And then other people can go along and vote for those ideas. So you can see that the more popular ideas will then be fed into the technology development cycle. And that helps you and it helps us to prioritize what we do with the software. So before I hand over to Mike, there's one poll question that I'd like to launch, and this is it. So are you seeing an increase in natural SuDS systems coming through. And I've got this in mind because of the fact that we have the change from SuDS for adoption to design and construction guidance. And as I mentioned, we're definitely reviewing at the minute the non-statutory technical standards as well. So I'll just give you another few seconds to vote on that. I can still see it jiggling through. Almost half the audience have voted in sort of 30 seconds. So I can see it changing from one to the other. So I'll leave it running just a little bit longer to try and get a high proportion of you to vote. So if you can select either the yes or the no. And then what I'll do is I'll close the poll. We're up to 84%, 85%. Thank you. So let's have a look at what we've got. I share the results. So 54% of those 54% are saying yes, and 46% are saying no. So there is a definite rise, but yeah, not a massive change at this minute in time. It'd be really interesting to rerun this poll in a few months' time, maybe 6 months' time, when the non-statutory technical standards have gone out as well. Lovely. Thank you very much for that. I hope you can all see my screen again now, because I couldn't quite see what was happening with the poll whilst I was running this. So to hand over to to Mike. Mike is the technical support manager for the organization. So he heads up technical support for client services across the EMEA region. Apart from Mike running through the presentation, which I believe, Mike, you've made a recording of for us to run, we've got Jessica Jeffries on board. So Jess is the drainage design product manager. So she looks after microdrainage, InfoDrainage development as we move forward. Myself here as EMEA innovation manager. And we've also got on board Mark Ellis. So Mark is the drainage design product solutions engineer. He's helping everyone at a sort of pre-sales stage on the technical side of things, looking at what they should be using as a technology to help them with their work. So what I'll do is I'll hand over to Mike if you want to introduce yourself, Mike, and set the scene, and then we can run through the actual training session.
Sure, thanks, Pete. So like Pete said, I manage the support team. We're based in Wallingford. There's 12 of us who are dedicated purely to answering people's questions and to providing training. So it'll be me or one of the team who you'll speak to if you ever contact us. I think we're going to play a video in a second. I did pre-record this. Two reasons for this. Firstly, I'm always nervous about doing these sort of presentations if anything goes wrong on the day, so I thought it was safer to record it in advance. Secondly, during the presentation, I run a simulation, run a series of storms through a network, and then look at the results. Now, this takes about 3.5 minutes to run the simulation, which is fine in the context of doing a study, but is an eternity if you're doing a live presentation. So purely for that reason, I recorded it, and then we've foreshortened that time during the presentation. But other than that, I recorded it live, did it in one take, and I'm around to answer questions at the end. So I think it's back to Pete to play the video.
Thanks, Mike. I'll play that now. So you can just confirm that you're seeing this once I hit the play button, and then, as Mike said, we'll have a Q&A for 30 minutes at the end of this audio. Thank you.
Hello, everybody. The first thing to mention about auditing is that we consider auditors to fall into two broad categories. Firstly, those who own the InfoDrainage software and will use that as a tool as part of the auditing process. And secondly, those people who don't necessarily own InfoDrainage but will just be looking at the printouts. That's okay too. What I'll be talking about on this presentation is what we've done with printouts and some of the new features that will help you complete the audits if that's all you're doing, if you're just looking at those printouts. One of the first things to mention is that we now have a neat utility for sending and receiving the data. So say you've just completed a project, you want to package it up to send it to the auditors. the way that we recommend you do that is through this transmit design feature. What that allows us to do is to create a zip file, which can obviously be unzipped once the auditor has received it, and then you get the options about what's going to be included in that zip file. So it may be just the model itself, or it may be all the results as well, all the associated data such as GIS, CAD data, could be the results as well, and the surface data. So I would say as auditors you should be looking for all of this information to be packaged up and sent to you in one go. Now when completing the audit, perhaps the first thing that we're looking for is simply that the model location is in the correct place. And one advantage of that with InfoDrainage is that graphics are very much front and center. So we can easily import background photos, background mapping, so that we can easily confirm that we are building our proposed scheme in the right place. I'd say there's two principal reasons why we want to know that we're in the right place. Firstly, rainfall varies across the country, so from that point of view it's important to be in the correct location. But also InfoDrainage works very much with surface information, so we need to understand the topography of the catchment so that our flow routes are in the right place. There's several methods of importing surface data, and I'll show an example of some surface data that I've imported here. So this was previously imported, just takes a few seconds to import that data. Can come in from a variety of sources. For example, there's data freely available over much of the country. There's a website you can download it from. It comes in what's called ASC format, which is then simply loaded into InfoDrainage. In other locations, maybe you're operating in a particular part of the country that doesn't have that data freely available, so you may be necessary to commission your own survey. It can also import that data. Thirdly, I'd give a shout out here for our XPSite 3D road design package. In that you design the roads, design the finished floor levels for the properties, design any other earthworks. Once you've completed your design in XPSite 3D, you can then export the final surface from there, and then that can be imported into InfoDrainage, and you use that as the basis of your flooding assessment. So the first thing I'm going to do is look at this initial flooding assessment that you might do once you've got your initial surface information. So what we've got is a facility called a deluge assessment. Now this is quite a simplistic assessment. All we're trying to do here is gain an initial understanding of the topography of the site. So we've got our imported surface information here. What we then do is divide that surface up into a number of grid squares, and I've chosen 4 meters by 4 meters. You can make it more accurate. It does mean that the analysis would take a little bit longer to complete. So for this demonstration I think 4 meters is a reasonable balance. And then what it's going to do is it's going to dump 50 millimeters of rainfall all at the same time right across the catchment. And that's why we call it this deluge assessment. You can imagine a large amount of rainfall landing simultaneously. And then what we're going to see is what happens after 60 minutes. Where is that rainfall after it's hit the catchment? According to the surface model, according to the topography, it's going to flow across the catchment surface, and it's going to accumulate in any low spots that it comes to. So this just gives us a good initial understanding of where the rainfall might accumulate. So what we've got excuse me, what we've got is the ability to plot simply the depth, or the depth times velocity function, which would give us an indication of any damage is going to be caused by water flowing across the catchment surface. But I guess the primary one that you're looking for is just the depth of water. So when we come to place our SuDS features, our other storage features, it's obvious that if we place them here, this would be naturally where water is going to accumulate anyway, so this would be a good location for them. Probably not a good place to build our properties and things like that. So it just gets a good overview of the site to start us with. Once we've done that, probably the next thing that we want to do, as I said, we can link to background mapping or photos of the area. But what we probably want to do then is to bring in our CAD CAD drawing of our proposed layout, and we can do some sort of assessment to see which properties may be affected by any flooding of the catchment surface. Perhaps we would look to build storage in these areas. It would highlight as a warning that this maybe isn't the greatest place to build some properties. Okay, so just a very initial outline assessment there. So we've got a general understanding of our site. We've got our proposed CAD layout of what it's going to look like. Now we start to build our InfoDrainage model. So perhaps the first thing that we would do is to locate our manholes. So we can see here we've got our manholes numbering system. This is one of the reasons for the new simulation engine that we've introduced. Perhaps I should have mentioned that at the start, but one of the key differences between microdrainage and InfoDrainage is that they use different simulation engines. So the underlying mathematics is different between them. What the main thing to emphasize with that is it's not as if one is right and the other's wrong. One's an improvement on the other, anything like that. They're just different underlying mathematics. It was necessary for us to do that in InfoDrainage because of some of the new features that we wanted to implement. And this is the first of those new features. We are not tied to the numbering system which existed within microdrainage. So we can have connectivity going in any directions. You can have flow splits, bifurcations, whatever you like. All of that is now possible, and we thought that was important to include that, and hence that was one of the reasons why we switched to a new simulation engine. I will also mention at this point that it is possible to import a microdrainage. So you might have a microdrainage study that you then want to audit within InfoDrainage. That's fine. You will get slightly different answers. They should be similar because the two methods of calculation are certainly similar, but there will be some differences, just as I say, because we've made the calculations, if you like, more flexible. There's more possibilities for things that you might want to include, and I'll mention that as we go through. Okay, but the first thing we do is to import the manholes, and one of the things that we can do is look at those manholes in a table. So we can open up a table, and we can open up a table of the junctions. So here we've got all the junctions. I'm just going to make this a little bit smaller, and we can customize what goes into these junctions. So for example, one of the most key things is that we might want to put in a cover level for each one. Now, one of the key things that you're looking at here is whether the cover level has been typed in by the user, or it's now possible to derive it from the background surface information. Okay, I'm just going to open my table back up. So in this table, we can see we've got perhaps the primary information is the cover level. Now, one of the first things with regard to an audit to note is that in this case the numbers are shown in red, and that means that they've been typed or copied in by the user at some point. The alternative to that would be if they were shown in blue, it would mean that they're being derived from the surface data. So there's a really neat feature within InfoDrainage in that if you place your manholes and there's a surface model already available, or if you subsequently import a surface information, it's going to ask you, do you want the cover levels to be derived from the surface data? And in the majority of cases, you would perhaps say yes. In this case, we're going to ask the question, why haven't we? Why aren't the cover levels taken from the surface information? It may be that it was imported from an old microdrainage model or derived from some other source, but at least it's a question worth asking, is how were those cover levels derived if not from the surrounding surface data? So I'd say that's one of the questions that you should be asking as part of the audit. Just understand where those cover levels came from. Okay, so that's one element. Another element is the connections, which we can switch on and off like that, and we can also look at those in a table, and the table's been automatically opened now. So one of the things is, again, I'd emphasize that we're not tied to the old microdrainage numbering system. I happened to create this model by importing an old microdrainage model, which came in very easily, but we're not tied to that naming convention. One of the things that we can see as well is that we're presented with both the upstream and downstream cover levels now. So each pipe, we see, I hope, everything that we need. This table can be customized as well to include other fields, things that we might want to see as part of that table. However, one of the key things that we're looking for, I would say, at this stage is this auto size feature. This works very similar to microdrainage. We hope that we've simplified it a bit in that generally with auto sizing you've got this padlock, and the padlock is either open or closed. So if the padlock is open, it means that it is available to be designed within InfoDrainage, and I'll be walking us through the design process in a second. If it's closed, then it means that the data's been typed in, and there are many reasons why you might want to do that. For example, there may be some other service like a gas pipe running across the catchment. You may need to avoid that, so you may need to type in the invert levels for a particular pipe. You may need to type in the size of a pipe if you're going to use it for storage, something like that. So there are many reasons why you would switch off the auto size feature and specify your own dimensions. But at audit, the question is going to be, why did you do that? You know, what was there a legitimate reason for doing that, or you know, what's the reason? That's part of the auditing process, is to understand what's gone on during the creation of this model. So that's so we've got our manholes, we've got our pipes which connect up the manholes. One thing to mention, I guess, is as good as time as any, is we look at the outfall details. So we've got the last pipes are generally draining down to this one location here. So we've got one outfall in this particular simple model, and we have some options. It can either freely discharge, or there may be a fixed surcharge level, or if we're discharging into perhaps a tidal location or a river, something like that, where the water level changes with time, we have that ability to put in this changing water level. And one of the things to mention here is that, again, this is why we've moved to a new simulation engine, because now the water does actually flow from the river, from the tidal estuary, whatever it is, back up the pipes. In microdrainage, there's a flat valve automatically placed on the last pipe in the system. So although an outfall can be locked in microdrainage, there's not the reverse flow from that downstream source. In InfoDrainage, there is. We do it all from that regard. We can apply a flat valve if we want to, but it's our choice. If we do, then the outfall would be locked and no water would be allowed to flow backwards up into it. If there's no flat valve, you get the water flowing backwards up into the system. And as I say, that was only possible with this new simulation engine. So we've defined our pipes, we've defined our manholes. Next thing to look at is the inflow locations. So very simply, these are our subcatchment boundaries, and again, this is available through the DrawNet feature of microdrainage, but here in InfoDrainage it's really sort of kind of front and center. This is the default way of producing our catchment locations. We would load up the CAD data in the background and then make an assessment about how these areas are going to be digitized. So using our skill and judgment as engineers, we would say, I think that this area drains to this particular manhole, and you can see helpfully there's a little icon and a little dotted line to tell us that this area drains to this manhole. So you know, just about the most important thing that we're going to do is to make sure that our inflows have been designed correctly. Now at this stage it's worth looking again at the tables, or we can just click on each individual item. I'll go with each individual item this time. So one of the things that's important is this percentage impervious. This is a key parameter that we need to review as part of the audit process. What we're saying here is essentially how much of the catchment is either concreted or tarmacked over. So because the assumption is that we're going to get the vast majority of our runoff is going to come from these developed areas. So you can see that using the graphics here, it's very easy to compare the background CAD data and to make an assessment. Some catchments may be more impermeable than others, and we could make a blanket assumption for all catchments, or we could do some more detailed analysis to say what is the percentage of impervious for each individual catchment. You know, it's our choice. How much time have we got? How important is it? But as part of the auditing process, you want to assess that. One of the things also, which is really important at this stage, is this volumetric runoff coefficient. So I could do a whole presentation just on this value, but essentially what we're saying is that once rainfall lands on this catchment, we're only going to consider runoff from 60% of it, because we only consider the runoff from the concreted and tarmacked and developed areas. And what we're saying is that of the rainfall that lands on that 60%, only 75%, or a factor of 0.75, only that amount gets into the manhole. So there is a lot of debate about this value. These are the default values that are available within both microdrainage and InfoDrainage, but lots of auditors would have a different view on this value. Some say it should be increased even as high as something like almost up to, say, a factor of 1, some people say. Now this is what we think is a very useful feature here. The useful feature is the use of project templates. So if I go to File and Object Templates here, what we have is, looking for example at the inflows, I've got a standard area, but if I want to, I can create my own area. So I might call this something like high runoff area. And what I would do is I might set the percentage of impermeable to be the standard 60 value. But say, for example, as a lead local authority, I've taken the decision that I want to have a higher volumetric runoff coefficient. That's going to be my standard. You can save that template, and then what happens is you can provide that template to your model builders. So what happens then is when they come to, so they may be looking at, you know, a new model, they may be looking at a model that's half built, but when they come to create their inflows, they then have to use this template. So I then drag out a new area that I may want to digitize. I then digitize the area which drains to this particular manhole, and we can see when we look at the characteristics of this that it already has my proposed volumetric runoff coefficient or percentage impervious. And I can apply this to anything. You know, if I want to use a pipe with a particular roughness, I want to use only manholes of a particular size, I can set them all up in templates, and then as a approving authority, I would provide that template to the to those who are going to be building the models that I'm subsequently going to audit, and I say, you know, your models must be built in accordance with these templates. So really sort of avoids the possibility of people using the wrong values if they stick to the templates. So templates, we think, is going to be a tremendous advantage to be used as part of the auditing process. Okay, so let's assume that I've now built my model. I've made use of the background surface data. That's been helpful in applying the cover levels from my manholes. I've used my background CAD data or other mapping data to define my subcatchment boundary. So I've already got a very good understanding of what's happening here. The next way that I might want to look at the data, an important part of the auditing process, are these flow paths. So what I would do there is right click and create a new flow path. And what I'm looking for essentially is the model connected up correctly? Because now that we have this kind of infinite flexibility in the way that our pipes are designed, where they connect, it would be possible to just miss a connection and have a model that's not connected up at one point. So an important part of the auditing process is to, sorry, I'll just create that. So add in a flow path. We can see we've got this square value. I'm going to click on a manhole there, zoom out and zoom down to where I think the outfall should be. And what I'm looking for firstly is just, do I have this green square? If I do, then it shows that these two locations are connected. So click on that and I've created my flow path. So this is an important check to say, is everything connected from here down to here? Once I've created that flow path, another advantage is that I can then view that as a profile view. So we can see what's happening at the moment. We can see that we've got our manhole levels, and we can also see graphically this is taking a section through the surface data that we loaded earlier. So this would be another visual check that your manhole levels match up with your surface information. It's also useful, it would allow us to spot any localized low points or anything like that if we want to comply with a, say for example, 1.2 meter depth of the pipes. Very useful visual check on all of that. So important to check those profiles as part of the auditing process. Okay, once we've done that, probably the next thing to move on to is actually designing the pipes. You know, we've now got confidence that all the data has been input correctly, so now we have to go through the actual pipe sizing process. So at this stage it's useful to now look at the rainfall that we're going to use. Very little has changed here really between microdrainage and InfoDrainage, so if you're familiar with the rainfall in microdrainage, there's not a huge amount to say here. We're compatible with FSR. The recommendation now is that FEH is now much more recent, so we would say that's generally, I think most approving authorities would define the use of FEH rainfall as being the most useful data available. The 2013 data, what we're going to do is set up our return periods. Now, designing a network, the important thing to recognize there is that designing a series of pipes is actually a two-stage process. There's effectively two tests which a network has to pass in order to be designed correctly. And this is according to what used to be called SuDS for adoption. I think now it's the Design and Construction Guidance. But in there it describes how it must pass two tests. The first test is a no surcharge test, and depending on your catchment and where it is, typically it's going to be about a 1 in 1 year or 1 in 2 year storm that it's going to have to pass. So I'm going to say 1 in 2 year in my example. So the idea is that during a 1 in 2 year storm we should get no surcharging in the catchment. Later on we're going to look at the second test, which is the no flood test. So up to a 1 in 30 year storm, it's okay for the pipes to surcharge as long as there's no catchment flooding. So it's very simply as long as the manholes don't flood. Now, of course, there is no such thing as just 1 2-year storm or 1 30-year storm. They can come in a variety of durations. So here's where we pick the durations. We have a vast array of durations. My personal thought is that it's very unlikely that the critical duration, in other words the worst storm, is going to be longer than a day. So generally I would say click this default button and that will click these 12 storms, which between them, kind of if you analyze these 12 storms, then you can have confidence that your design would work for any storm duration. So pick your storm durations, pick your return period. There is a difference between summer and winter storms. They have different profile shapes, and also our assumption is that generally during the summer the catchment is drier and therefore less rainfall that lands on the catchment would get into the sewers, whereas during the winter a lot more heavy storms and therefore the catchment is going to be saturated and therefore the amount of runoff is likely to be higher. So different shaped storms but also different proportions of runoff. So for those reasons I won't go into the details. We talk about this in detail on the auditing training course, but it is important to analyze both the summer and the winter storms. Okay, so we've set up our storms. Yep, I'm going to save those changes. And then the next thing is to actually look at the design process. So as I said, two tests, a no surcharge test and a no flooding test. Firstly, we're going to look at the no surcharge test. So we look at the network design criteria. The first thing we're being asked for is what type of rainfall we're going to use, and as I just showed, we set up a 1 in 2 year storm for that. And then secondly, we set up these design options. A lot of parallels here between microdrainage and InfoDrainage. The other thing to mention at this point is we are currently updating this. We're improving it. There is going to be changes to this feature in particular over the next few weeks. So by the early 2021 it will work slightly differently, basically we're improving it. We're always developing the software. But the thing to mention for now is very similar to microdrainage. You set up your rules in terms of how deep the pipe should be, a minimum cover level. You give them a minimum and a maximum slope. The main thing I would say is that we now allow backdrops. There's much more emphasis on backdrops. Now I know that a lot of approving authorities say that you shouldn't use backdrops. You know, if that's your view, then fine, you just untick the box. In some steep catchments, then it's difficult to know what the alternative is. You know, you have no alternative other than to lay the pipes at very steep slopes, which is going to create some high velocities and therefore the potential for damage within the sewer system. So so a lot of, you know, sometimes you need to use backdrops in certain situations, and if you do, there is now an emphasis on those. You can put them in and it will be designed to those required settings that we have in here. Just as we have in microdrainage, we have standard manhole size libraries and also standard pipe sizes. So what we're saying is that the smallest pipe I'm going to allow is 100 millimeters, although I could delete that if I don't allow the use of 100 millimeters. Then it goes up to 150, and then basically it goes up in 75 mil increments. So 225, 300, 375, 450. You can edit that if you want to, but that's how it's set up. Once we set up our criteria, we have quite a neat little wizard that it walks you through. So the first thing it's asking you for is what's the flow path. So we design one run of pipes, one branch of pipes at a time. So in my case, very, very simple because I've only got one branch. But if I had a more complex network, you can imagine with these flow splits and bifurcations and that sort of thing, it's important that we recognize which series of pipes we're designing at one go. We then ask for the details that I've just set up in the network design criteria in terms of the rain and the rules under which the pipes are going to be designed. And then it goes through and it gives me a report. And as I say, I identified a couple of warnings, and that's where we're working at the moment to resolve those warnings essentially. But we go through, finish our design. It gives me a network design report. So as auditors, this is what we're looking for. We're asking for the network design report, and that'll simply tell us the size of each pipe and the diameter, the other features that we've got. One of the useful things that we've got here is the capacity against the flow. So for example, in this top pipe here, according to our analysis under a 1 in 2 year storm, we had a maximum of 9.133 litres a second going through this pipe. The capacity of this size at this gradient has a maximum capacity of 11.55. So we can see that there's a little bit of available capacity in this top pipe, but not a lot. If we looked at the second pipe down, we would see that there's currently only 15.4 litres a second as a maximum flow through it, whereas it has a capacity of 27.6. So much more scope for increased capacity in this pipe. So if we were to build some more buildings and apply them to the network, maybe avoid the top pipe but allow them to the second pipe. Of course, you then got to assess what the knock-on effect is going to be right down the model, but you get the idea. It's a useful assessment to see how close we are to surcharging those pipes under the current regime and take it from there. Okay, so the next item is going to be once we've done that, we can then go back to the flow path and look at the profile, and you can see in this situation it's introduced some backdrops into this analysis, so we can see how the pipes have been redesigned, and we can get the characteristics, manhole cover levels, all that kind of stuff is produced in a table below, so useful in our analysis. Okay, so the next thing I'm going to do is I'm going to move on. We've passed the first test now. We've completed our no surcharge test. And the next thing to do is to move on to a full design, a no flood analysis. So I'm going to move to a slightly more complex model now. So this is a model that covers the whole catchment. And in here I've got some stormwater controls as well. Now this was perhaps the primary reason why we switched to a new simulation engine, was to allow more complex representation of SuDS. And in particular, well, firstly, we can see there's 3 SuDS features in this particular catchment: a permeable pavement here, a swale here, and a pond here. And immediately we can see one of the advantages is that we actually digitize the outline of a particular structure. So rather than just typing it in its dimensions, of course we have its dimensions if we want to review those, but in addition to typing its dimensions, we can also see a visual representation of where it's going to go. So extremely important in understanding how it's all going to kind of fit together. One thing I'd like to emphasize to you in particular though is how the complexity of our SuDS structures has increased. And again, there will be presentations and training courses entirely on SuDS structures. But for now, just to introduce it, I would say that one of the things we've got here is a swale. And swales have the ability to have both a trench and an underdrain. So one useful feature is we've got a picture of what each SuDS structure looks like. And we can see here that there's really sort of 3 separate elements to this swale. You've got a kind of open bit at the top where water will flow through. So this is kind of like a sort of rough pipe. So although the flow is free surface flowing through here, because we've got this grassy edge to it, it's going to be fairly rough, and that would be reflected in the Manning's coefficient that we would type in for it. We've then got we can then choose to have a trench as well. So that's going to be gravel flow through here. So obviously the flow regime through a gravel trench is very different than an open channel. And we've got specific flow equations for dealing with flow through gravel. And crucially as well, we've started to provide advice on what the parameters, basically what the conductivity through gravel would be. Now this is a big step forward, but I'll be honest and say this type of technology is still in its infancy. What we're really looking for is sites around the country where people have installed SuDS features, monitored them over a long period to increase our understanding as a software company, but also industry understanding of how these things operate, in particular how they operate over long periods, what happens if you do and don't maintain them, that sort of thing. But we have separate flow equations through the gravel. And then we have perforated pipe here, so the water flows down from the gravel into the pipe and then flows out through the pipe. So there's essentially 3 different flow regimes going on here. The open flow in the swale itself, the flow through the gravel, and the flow through the pipe. And what we've got the ability to do is to have interaction between these 3 flow regimes along the length of the pipe. And honestly, this is really groundbreaking for us. This ability to have flow moving from the gravel to the pipe to the swale all the way along its length is something that we haven't done before. It's not in any other software. It's not even in our advanced InfoWorks ICM software. Doesn't have this ability yet. We think we're the first people who've managed to sort of crack the mathematics on this. We've got some really clever mathematicians based in Wallingford who've devised this. But this is really huge. We think this is the first time we can represent these types of structures properly. So for that reason, that was a major reason why we had to move to a new simulation engine to allow this. So as auditors now, you've got to assess all of this. You've got to say, is your representation of the swale correctly done? Is the representation of the gravel? And have we got the correct representation of the permeable pipes? But there's going to be a lot more on this. This is obviously the future of design. Is how we represent all this. Okay, so we've similarly just show you quickly the permeable paving, and again we have an image which helps us define what the parameters here relate to in terms of defining the characteristics of this structure. Okay, so we've now got all our pipes which have been designed to meet the 1 in 2 year surcharge criteria, and we now want to assess them for the no flooding criteria. So what we do for that now, same rainfall. I'm just going to, all I need to do is in the rainfall manager, I need to tell it that now I've stopped using the analysis for the 1 in 2 year, and I'm now going to put in the analysis for the 1 in 30 year. If we wanted to include climate change for either of these, that's where you do it. And again, an important part of the auditing process is if you want climate change to check that it has actually been applied. We then come through to the analysis criteria. In here, it's telling us how many separate storms we're going to run. Here we get to choose how often we export the results. 2 minutes is fairly typical. What we're saying is we're going to produce graphs, and there's going to be a point on those graphs every 2 minutes. We have a distinction between flooding and flood risk, and we can specify that margin. So essentially what we're saying here is if the water gets within 300 millimeters of the cover level, that will be counted as a flood risk. That's where you'd specify it there. The other thing to mention, a new feature, and we now specifically represent urban creep. So urban creep, I'm sure you know, but it's how a catchment becomes more urbanized over time. So people will tend to build conservatories on the back of their houses. They'll tend to tarmac over their front gardens and turn them into carports. So there is a theory that over time a catchment will become more and more urbanized, and sometimes it's included in audit considerations that there must be a factor included for urban creep. So it was available in microdrainage. It's now specifically represented within InfoDrainage. Okay, so we've set up our analysis criteria. What we then do is go through and run a validation. This can be done at any stage. What this is checking is just making sure that everything's sensible, making sure that every inflow is connected to a manhole. It's making sure that every manhole has a cover level specified, every pipe has a roughness and an invert level, those sort of basic information. So it's saying, okay, have we typed in, have we got at least a parameter for everything? And now what we're going to do is do some analysis and see whether those parameters have actually worked to make our design acceptable. Okay, so I go through the analysis, simply press go. Right, I've got a confession to make at this point. We're running 18 storms in a catchment which is about 35 pipes, and this takes about 3 or 4 minutes to run, which I suggest is acceptable when you're doing an analysis, but it's an awful long time to sit and watch it when you're doing a presentation. So I'm going to foreshorten this process. Okay, so my analysis is completed now, and I'm now looking at a summary of the 3 storage features that I have within the catchment. So my swale, I've got a permeable car park up here, and I've got a pond structure down here. So I'm looking at whether these are full or not, basically. So we've got a nice button here. As I said, we've run 18 storms through these of varying durations, summer and winter. So what we want to do now is to pick essentially the worst storm. And what we can see is that we've got a different storm for each structure. So for the pond it's the 240-minute storm, for the swale it's the 360, and for the porous paving it's the 120-minute winter storm, which was the worst. And for each one we can see what percentage of the structure was available. So we can see that that pond is very nearly full. We can see that the other 2 structures have capacity available. So 2 things that we could potentially do here is 1, reduce the size of these structures, or 2, we could limit their pass forward even further, because I've got orifices or other flow control structures, hydro brakes, that sort of thing placed at the downstream end of these structures, which would limit the flow. So I could limit the flow, store more in these, and therefore potentially reduce the size of the pond down here if that's what I chose to do. So this critical storm analysis is crucial in our assessment of whether these structures are working or not. Now, one thing I can't get away with is get away without mentioning this big red sentence here. So it says the results show convergent was difficult for the analysis. Please review the design. So this is an issue which we describe as instabilities. Now this is something which affects InfoDrainage, it affects microdrainage, it affects all our other modelling packages, it affects pretty much, I would say it affects every modelling package there is. It's just saying there is the potential that perhaps the mathematics hadn't added up in this case. For those of you who are familiar with microdrainage, you'll know that there's a process that we go through. One of the crucial processes is looking at the graphs to see if there's a lot of oscillations within those graphs. So the same process we go through here. We allow the graphing tools to help you get to the bottom of this, any messages like this. If you can't solve it, then that's where the support team comes in. Send the model to us, transmit that design, send it to us, and we'll try and sort it out for you. Two further things to mention is, one, we work on the simulation all the time. As I say, we've got some really smart mathematicians whose job it is to improve this, and that's what they're doing. Secondly, this is quite a new software package, and from looking at these messages so far and digging into why they're occurring, my feeling at the moment is that they're popping up more often than they should. So at the moment we're getting these messages, we're investigating the models, and we're finding there's not actually anything wrong with them. The models are acceptable. So for now, I would say if you see this message, by all means contact support. We'll do our best to sort it out. We're working on it, but our advice is quite likely to be actually everything's okay, and just the tolerances which make that message appear are probably a bit too tight at the moment. But as I say, it's an issue. We will always have issues with instability. It's not as if there's a perfect system out there. It's always evolving, but we work on it continuously. Okay, so we looked at our structures. We find that they're okay. One question to address at this point is, how do we limit the flow coming out of the pond? Now, the first thing to understand is how we derive that limit, and it can be derived in a number of different ways. Different approving authorities, or whoever you're discharging into, so it might be the water company, somebody will have a view on how much you're allowed to discharge from this new system that you're designing. If you happen to want to use the rural runoff calculations, then they used to be, well, they still are, in a separate source control within the microdrainage environment. Here they're built into InfoDrainage as well. So the same system. What we're doing is choosing the method by which we're going to make our greenfield assessment. So you can see it goes from everything from ICP SuDS through to the perhaps over complex in this case. It's unlikely that you'd want to go to the complexity of RefH2 for a new building assessment. This is more for river studies. But essentially you have a choice of which method you're going to use, and then you choose your parameters. You pick where you are in the country based on the map. This will bring up parameters such as average annual rainfall and the soil type which exists in the catchment. That's because we understand that, say for example, a sandy soil, there's likely to be less runoff from that than there was from a clay type soil. So one way or another, we develop our greenfield runoff, and it's going to give us some sort of limit of discharge. And the one that a lot of people work to is this Q bar value. Again, we have training courses which go into the details of where these values come from and how they should be derived. But essentially for this presentation, I'm just going to stick with the fact that we've done some sort of greenfield assessment, and we've got this Q bar value of, in this case, 16.1 litres a second. So we would then look at our final control structure, discharging from the catchment. Look at the outlets, and this actually has two. We've got an orifice, and the orifice has been sized. There's an automatic calculator in here. The orifice has been sized such that as the pond becomes full, the limit of discharge is 16.1 litres a second. So a common way of limiting flows, hydro brakes would be another way. But essentially we're setting that up such that when the pond is full, we don't exceed the limit of discharge. What's going to happen instead is that when the pond becomes full, it's going to discharge via an overflow weir, and here we get to define the characteristics of that weir, and we get to see it graphically. So we've got an orifice which goes this way to the outfall, and we've got a weir that spills out to perhaps a secondary outfall here. What we then want to do is, when we look at the results, we then obviously want to see whether this limit of discharge is exceeded. So what we can do is look at any of our connections, look at the last connection in the system, which in this case happens to be 1016, and then we've got some graphs which can show us for any particular storm whether that limit of discharge is exceeded. And again, going back to this idea of looking at all your stormwater controls and then picking the critical storm, you obviously want to base your assessment around these critical storms. And I'd say, you know, that's the bulk of it. So we're looking to make sure that manholes don't flood. We can look at a summary of our inflows. We can look at the critical storms for those as well. We're making sure there's no flooding during in the catchment. We're making sure that our storage structures don't become overwhelmed. We're looking at all those things, and I hope the tools to do that are here. A couple of sort of separate, neat little features to mention is, firstly, we have this audit report. So what this will do is it'll take you through and actually focus on specific parts that you may want to audit. Now, again, a few things to mention here. I set this up in advance, saved the model, and then reopened it, and these tick boxes have been remembered. So my message to you as auditors is work with the templates. So if you want something defined in a particular way, work with those templates and then provide those to the contractors who are going to be producing the models. But also you can provide them with a template in terms of how you want this audit report to appear. So you create an audit report, save it, and then provide that, and then you say to them, you know, when you submit your audit, I want to see these particular boxes ticked because I'm going to be looking at, for example, pipe length. I'm going to make sure that no pipes are between a tolerance that I've decided could be between no shorter than 5 meters and no longer than 100 meters. I can check my discharge rates. So here I could specify what a maximum discharge rate is, for example. We've got all these types of things. For example, I'm not going to allow the use of 100 millimeter diameter pipes. So I set up all the choices that I want to make about how a model is going to be created, essentially, and then I perform that audit. It produces me a little report, and then I can run through, and crucially, you can identify whether there's any problems, and it's identified a problem with the discharge rate. So maybe in this case I set the tolerances, actually I haven't set a tolerance at all, so as soon as it exceeded 0 it was going to flag that up as an error. But I hope you can see the principle is that you set up the tolerances that you want to achieve, the items that must be within certain parameters. You then run the audit report and it tells you if there's any problems, and it gives you a summary of the audit outputs. Whether they passed or failed, they would then be included in this report. So essentially a useful tool to make the submission standardized, so you always get data presented in a way that you can control. In addition to that, there is also the ability, obviously, to do standard printouts. So the first thing to mention is that hard copy headings are now kind of much more obvious, much more front and center. So what we would do then is put into our hard copy headings, we can see that we could give the project a title, the company address. You can type anything into that now. You're not tied to the licensing arrangements for this. So whoever did this piece of work should put their details in there. And I'm going to say that one of my colleagues, Mark Ellis, he was the person who originally did this. And then let's say that I was the person who checked it. I'll put my name to that. Okay. And then what we do is we go in and produce a printout. And again, the thing to emphasize here is that you can decide which areas you want to see in the printouts, and then save these options and then to provide them to your contractors, because that's the key thing, is that you always want to receive the data in a very standardized format. To be slightly cynical for a second, I would say that there's two ways in which contractors can kind of pull the wool over the auditor's eyes. One would be not to provide the necessary information, but the other would be to provide too much information, to just deluge an auditor with information that's then difficult to pick through. So using this method, essentially you can say, this is the information that I want and this is the information that I don't want. So for example, what we can see is there may be different phases to the study, and I've used 2 phases. I used an initial build phase and then an optimized stage. When it comes to assessing this, I probably don't want to see the details of how the model was built. I just want to see what the final results are, so I can choose which ones of those I do and don't include. I can include the entire model or just particular parts of the model through the use of flow paths. You can say, do you want to see all the storms or just the critical storms? And I think this is a tremendous improvement in that it's no longer necessary or no longer sort of aimed towards producing hundreds and hundreds of graphs. We really only want to see the graphs associated with the critical storms. I'd mention here instabilities again, if you want to see those graphs, to make sure you're looking for a kind of smooth graph. If you see a lot of oscillations, then that's a potential instability that should be investigated by our support team based in Wallingford. But generally you just want to see the critical storms, and then perhaps you want to see the details of each individual inflow. You want to see where it is, what its size were, but likely you just want to see a summary of where all the areas are. You're also going to be asking for a printout to show this is in the right place. So you're going to be assessing where these boundaries have been digitized anyway. So possibly you just want to see an area summary, but it's your choice. When it comes to the results as well, I've said I don't want to necessarily see the runoff from every single subcatchment. I could if I wanted to. Really, I'm just interested in what happens within each pipe. I probably perhaps also want to see the stormwater controls as well. But essentially I have entire control over how this report is generated. I then update the preview, goes away. It's doing a lot of information here. It's analysing all the 18 storms, taking the critical information from it. We can see now that at the top here we've recorded who designed it and who checked it. That's on every page. Excuse me. One of the neat things we have is we now have manhole schedules to show what's going on. There's a lot of those, so maybe I would have chosen not to include them. As I say, it's entirely up to the auditor. Just going to scroll through all of those. So there's one for every single manhole. We can then see the details. As I said, this is the area summary, so we can see what choices were made about the impervious percentage. I should have perhaps added in that CV value into there. I can customize it to include that. I hadn't in this case, but you can make an assessment of all your areas. Gives you a summary of the total area at the bottom, which is often useful. That should be checked against the greenfield calculations, making sure that for example, people haven't included more area in their greenfield calculations than they have in their subsequent developed calculations. What we've also got is details of how the pipes were designed, crucially what type of rainfall was used. Are they using the more recent FEH rainfall as we recommend? What was our pipe library? All that kind of stuff. What else is useful? We want to see the details of our outfalls. There was 2 outfalls in our case. One was the main outfall leading through via the orifice out to the main outfall, and then we had that weir overflow. So we want to check if there was to be a tidal value included, you'd be looking for that there. There's one other thing that I wanted to highlight to you. Where is it? Oh yeah, this is one of the key things, is how the greenfield calculations were conducted, and then crucially we get on to were the storage structures big enough? Were the pipes all okay? We're looking to see that there's no flooding from these pipes. Because we were running with the 1 in 30 years storm, it's acceptable to surcharge but not acceptable to flood, so we'd be looking for that there. Just scroll through that. Looks all okay, but I would investigate any flooding. And then finally we get to the graphs, and we can see this is why we've got this. This does look a little unstable, and we would investigate why this is happening. What we're showing though is crucially that the pond fills up and then drains away smoothly. So I don't think these little local oscillations are affecting it, but it is something that we would want to investigate. So you can see, crucially, you can see what's happening during each of the critical storms. So like I said, very important that we hope that you're getting all the information you need without being inundated with lots of information that you don't need. So I guess the main message is that it is now entirely within your control as auditors. You can specify the templates for how stuff should be created, and you have entire control over the outputs that should be produced and sent to you, whether that's through using the template to make sure that whether that's using the file transfer to make sure that you are sent absolutely all the information that you need, or whether it's through customizing these printouts to make sure that they give you everything you need. So basically the power is in your hands to specify exactly how these projects should be completed and the outputs that you expect. Okay, so I think it's useful to end with an auditing checklist. Now, I'm not saying that this is an exhaustive list, but I hope it's useful to give you a start on the sort of things that you should be looking out for. So the first thing is you need to get all the data. So this is going to be the design itself, the model. It's going to be the background mapping, the background surface data, and any of the results. So the easiest way to get that is via the transmit design feature that's included, so it'll all be zipped up, and then when you receive it you can unzip it and it'll all be there in the correct locations. Secondly, check the location of the study. We have this ability now to use Google Earth, Google Maps, other sort of mapping data just to make sure we're in the right location, so that's crucial just to get a feel for the site, and also the fact that rainfall varies across the country, so you need to be in the right location. Number 3 is understand the surface information. So I talked previously about how it's possible to get this information for free for some parts of the country. However, I should stress that that would be the greenfield site, so prior to development. What you really need is the final surface, so the developed site. So we'd love you to use our product XP Site 3D to get the road levels and the finished floor levels for the properties, all that kind of information. But wherever it comes from, that's what you're looking for. It's the developed site levels, which is going to form the basis of your surface information. This fourth item 4 is this deluge analysis. I'd say this is optional, but it is a good idea just to get a sort of initial feel for the site. Where is the water going to accumulate that lands on the site? We want to sort of design our SuDS features so they naturally collect the water. We want to design our critical infrastructure, our housing, so that it avoids areas where water is going to accumulate. So get a good understanding, initial understanding of the site. And whether you do that or whether you don't, the next thing is going to be to have a look at your CAD information. So this is going to be likely to be the layout of where the roads and the houses are going to be, and that obviously wants to link in with the surface data. So by the time you get to point 5, you should have sort of collected all the critical data that's to be used on the study, and then you can get into checking the model itself. So number 6 is check the manholes. Remember about the cover levels. So we would expect those cover levels to be derived from the final surface data. If they don't, it's not necessarily an error, but you should be asking the question, if they didn't come from the final surface, then where are they coming from? And you're looking for justification for that. Item 7 is check the connectivity. So remember that InfoDrainage now, we're not tied to any sort of connectivity. Basically, we can connect anything to anything. So along with the flexibility comes a requirement that you have to check that it is all connected up. So remember to use the flow profiles, look at manholes at the top of the catchment, and make sure that they're connected to your main outfalls. Also through that process you can then create a profile to check the long sections, which comes in handy throughout the project. Along with that, you're then going to check the outfalls, and in particular if you're operating in some sort of tidal zone or somewhere else where the downstream receiving watercourse could impact your design, then we now have the ability to fully represent that. So you want to be looking to see if there are any of those backwater effects and how they've been represented. Number 9 is absolutely crucial. It's probably the fundamental part of any drainage study, is you've got to determine which areas are going to drain to your new network that you're designing. So have they been defined correctly? What's the evidence of that? you're looking for a map of the catchment divided up into those contributing areas. And now remember that we have a feature to check which area has been connected to which manhole. So you're looking for that evidence. Number 10, how has PIMP been defined? So crucial to the runoff calculations is knowing how much of the catchment is impermeable and how much is permeable, because the assumption is that we only get runoff from our impermeable areas. So in some cases you can make a blanket assumption about how impermeable a catchment is. In others you might be looking for some more detail, comparing it with the CAD data to say, you know, this area of the catchment is particularly impermeable, and therefore I would expect to see a higher value applied to these contributing areas. Number 11 is, what is the decision on the coefficient of runoff? So we remember the standard values in InfoDrainage is 75% runoff in the summer, 84% in the winter. Is that acceptable? That's really, you know, it's part of the study to understand that. I've said sort of anecdotally that we believe that maybe in high clay catchments where some of the permeable areas giving us runoff, particularly during a period of heavy rain when the ground is saturated, then perhaps you want to look in detail about whether those values should be increased. So once you get to a point 11, you're looking for evidence basically that all the kind of assumptions that are going into the pipe design are correct. And then in number 12 you're asking, what was the actual design process? So firstly, remember that it is a two-stage process. A model, according to SuDS for adoption or the design and construction guidance, has to pass two tests, a no surcharge test and a no flood test. So does it pass both of those tests? There are now powerful facilities within InfoDrainage to design the pipes, so have those been used? If not, again, it's not necessarily wrong, but the question is why not? What was the approach that the designer took if it wasn't the auto-sizing feature that's available within InfoDrainage? Crucially, obviously, which rainfall was used. Remember that FEH is now the most recent data, so has that been used, and is it appropriate to be used? Time of entry, fairly standard. That's how long the water takes between landing on the ground and making it to the manhole. There's a table in the Wallingford procedure which describes that. So is it in accordance with that sort of definitive advice about time of entry? Are we complying with minimum cover level? So this is where the design and construction guidance comes in. Pipes need to be a certain depth in the ground. It's typically 1.2 meters, may vary depending on what's happening on the surface, but very simply, are your pipes deep enough? If not, then you may need to look at some sort of protection for those pipes, additional concreted protection. But again, you're asking the questions about, is that right? I mentioned about backdrops. So in very steep sites, maybe you need to use backdrops. If not, then what are the velocities that are being predicted? Could those velocities cause problems with damage? You know, if you've got a high velocity hitting a very steep bend in the pipes, then that energy's got to go somewhere. And G there right at the bottom, if you're using the printout, so we'd obviously love you to use the software as part of the audit process, but if you are just looking at the printouts, remember there is a specific network design report that can be exported. So you're looking for that network design report. Remember about the capacity issues. Some pipes will be close to their capacity, other pipes may have spare capacity that would be useful if there's going to be further development of the site. So at that stage, you've run through the sort of automated process for designing the pipes. So you've passed stage 1 of the two tests. The second test, the no flood analysis. So again, you've got to pick a storm. Remember that it's not just one storm. There's going to be a variety of durations, summer and winter. So make sure they've all been run. And D there says focus on the critical storm. Again, that means don't allow yourselves to be deluged with thousands of graphs. You want to be very dictating what information is sent to you, and typically you only want to see the critical storms. Has climate change been allowed for? It's not always required, but if you specified that it is, it's your choice, and then it's your job to make sure that it has been included. Similarly, urban creep. Remember, there's a specific place now in InfoDrainage for urban creep. So at this stage, we think we've designed all the pipes so that they don't flood, don't surcharge. They've passed the 2 tests. The next stage is looking at any storage that's required. So somewhere downstream, it's maybe you as the approving authority own the receiving watercourse. You're in charge of the receiving watercourse. It may be that the water company defines it, but somebody is going to define a limit of discharge from the site. So the question is there, how was that derived? There are some tools available within InfoDrainage. You can choose to use them. I would say there's not one definitive approach to this. Again, it's open to looking at guidance and thinking what's sensible. It may be the greenfield runoff, it may be the brownfield runoff. But number 15 is, once you have a defined runoff, remember, just typing that into the software, whether it's InfoDrainage or microdrainage, does not absolutely guarantee that that's going to be the limit of discharge. If the water depth upstream of your flow control device goes above the design depth, then you will simply get more flow through that controlling device. So although a limit of discharge has been defined, you've then got to make sure that it hasn't been exceeded. So use the graph tools for this to make sure that the limit of discharge hasn't been exceeded. Number 16 is looking at SuDS structures. And as I mentioned on the talk, things are getting more and more complicated now. We have the ability now to represent a vast variety of flow regimes, whether it's free surface in a swale, whether it's flow through gravel media, or whether it's flow through pipes, including perforated pipes, which exist at the bottom of structures. So this is a fairly new industry. We are still feeling our way in terms of our representation of these complex structures. So have you built enough factors of safety in there to account for the fact that there is no sort of perfect system, and there's unlikely to ever be a perfect system of representing what we see in reality in a hydraulic model. A couple of things I haven't mentioned there should be on this list is, number one, make sure you check for instabilities. Despite our best efforts, some models do become unstable, so use the graphs for oscillations in the flow. If you find any, get in touch with the support team and we'll help you work through them. There's one other thing, the MAD factor. Remember the manhole addition? This is a correction factor to represent all those little house connections which exist in reality but not necessarily in the model. So as I said, this list will always be evolving as our understanding of how to represent these things improves and how the software develops and our processes and your processes develop over time. So that, I hope that's a start. So that's if you're using the software. If you only have the printouts available to you, then remember that we can easily customize the headings of these. So you want to know who did the work, who checked it. And the main message is now that it's totally within your control. So for example, you can define what goes into those printouts. In the same way, remember that we can define through the use of templates how things are constructed. So if you have a particular pipe roughness, a particular pimp value, a particular coefficient of runoff that you want to use, save them as templates, bundle it all up into an InfoDrainage model and actually send that InfoDrainage model. Say, here's a blank sheet effectively, here's where I want you to start, you build your model from this, and then there's really no arguments about those types of coefficients. So the control is with you. Remember I said that there's two ways that auditors can struggle. One is that if they're not sent enough information, and the other is if they're sent too much information. So remember that we now have the ability just to look at the critical storms, just to get the graphs from those, rather than getting the hundreds of graphs from all storms. So look at phases and look at storms. Only look for the stuff that you really need. And then you're going to look for things like, and this is just a suggestion, you're probably going to want to see the details of the manholes. You're probably going to want to see the details of the areas. So along with the summary, you certainly want to see a map of the catchment with the contributing areas defined. You want to understand how the pipes were designed, how the outfalls were included, and when it comes to analysis criteria, again, the question is what storm was used, what duration turned out to be critical, that sort of thing. H is the calculators. So that covers how was the limit of discharge calculated. And then finally, you're looking for that all to be summarized in the stormwater and connection summary, along with the structures summary and any graphs associated with that. But the main message is that
it's now totally within your control. So look at what you need, define that, and then send that out in the form of a template, and tick the boxes that you need on to produce the printouts. So that's it. That's it from me. Thank you very much.
At the end of the presentation here now, thanks, Mike. I really appreciate it, and just like to sort of thank you and Jess and Mark in the wings there for sitting in, and for everyone attending. There is a survey coming out that Ben from the marketing department has mentioned. So if people can respond to the survey, what we'll do is we will send out the checklist, but we can add the link in for the user voice is what I'm thinking, so people can kind of go there and raise any kind of issues at all. So thanks very much, folks. We're just 2 minutes over time, and have a great afternoon, and look forward to engaging with you in the future. Do let us know how you felt about the session, and we can maybe look at doing something again in the future with you. Take care and have a good day. Bye for now.